thank you very much. And on behalf of the participants, I would like to thank the organizers of this very interesting conference, Shuyung, KG, Claire, thank you very much. And also, of course, Mukai Chen, who is not here, but who also put lots of effort into this thing. So, and the National Taiwan University for Hospitality. Thanks a lot. Yeah, so I will speak about Mukai models, and this is a joint work with Aaron Bayer and Emmanuel Macri. It's kind of embarrassing to talk about this in front of Mukai. Yeah. Yeah, so actually our goal was to write down a proof of the theorem that Mukai explained and which was very important and useful for the study of Fano threefolds and high-dimensional Fano varieties. So let me give you a rough statement of the theory. So if X is a smooth Fano threefold with the Picard group generated by the canonical class. And in this case, you can define the genus. So the genus of X is defined by the equality that the cube of the anti-canonical class is equal to 2g of X minus 2. So this is the definition of the genus. So this is called the genus of X. So assume that X is a smooth Fano threefold with a Picard group generated by the canonical class and of genus 7, 8, 9, 10, or 12. So essentially this is equivalent to genus being at least 7. Then X is a linear section of one of very special varieties by a linear projective space of dimension g plus 1. Here mg are the following varieties. So when G is 7, this is the orthogonal Grassmannian 5, 10. So you fix a 10-dimensional vector space, you fix a non-degenerate quadratic form on this vector space, you consider the Grassmannian of 5-dimensional isotropic subspaces, and you take one of the two connected components of this variety. So for genus 8, this is Grassmannian 2,6, a very familiar variety. For genus 9, this is Lagrangian Grassmannian 3,6. So you fix a 6-dimensional vector space, endow it with a symplectic form, and then consider all isotropic 3-dimensional subspaces. So for genus 10, this is also a homogeneous variety, but it is homogeneous for the algebraic group of Dynkin type G2. And it sits naturally inside Grassmannian 2,7. So I will use notation G2 Grassmannian 2,7 for it. I will maybe say a bit later how it can be defined explicitly. For now it doesn't matter much. The important thing is that this is a smooth homogeneous variety. And for genus 12, you consider Grassmannian 3,7. And now you endow this 7-dimensional vector space with a 3-dimensional space of skew-symmetric forms, and you consider all 3-dimensional subspaces which are isotropic for all these 3 forms at the same time. And I denote this by E3 Grassmannian 3,7. So it is 3 isotropic, tri-isotropic Grassmannian. In a contrast to the previous cases, this is not a homogeneous variety. In fact, there is a 6-dimensional family of such varieties. Okay, these are MG, and each of them has a natural projective embedding. So this guy lives in P15 by the spinor embedding, which is given by the 1/2 of the restriction of the Plücker bundle from the Grassmannian 510. So it's a feature of this situation is that if you restrict the Plücker polarization, it will be divisible by 2, and it is still a very ample line bundle, and it gives an embedding into P15, and this 15-dimensional projective space corresponds to the 16-dimensional spinor, half-spinor representation of the corresponding group. So this guy lives in P14 by the Plücker embedding. This guy lives in P13, again by the minimal ample line bundle. This also lives in P13, and this is the projectivization of the joint representation of G2, and this also lives in P13. And now, in the statement of the theorem, you just choose a sufficiently general projective subspace in one of these projective spaces, and you intersect and you get your X. So this theorem is very powerful. It gives you a full control of the geometry of X. It is another great property of this construction is that it is canonical, so it gives you full control of the automorphism group of X and of everything. So this is maybe the most useful fact about Fano threefolds that you can imagine. You mean smaller G or higher G? There are also Mukai models for some K3 surfaces of higher genus, but they do not extend to Fano threefolds, so I do not discuss them. Okay, this theorem was proved by Mukai maybe 35 years ago already, right? I think 89 or something like that. Yeah, but and many people use this theorem since then, but I mean, the full proof wasn't written down, at least in English. I don't know, maybe there is something in Japanese. Yeah, so, I mean, I was using this theorem since my PhDs, so also for a long time. And starting from some moment, people started asking me, how do you prove this? And my typical answer was, come on, Mukai proved it. But then, at some point, I thought that maybe it makes sense to write things down, and this is what we... Yeah, I will say a few words about extensions of this theorem also, yeah. Okay, and this is what we finally did with Arendt and Emanuele. And so for the most part of the proof, we use the ideas that can be found in the papers by Mukai, but we also came with a few simplifying tricks, which are kind of nice, and which, at least for us, they give some nice explanation of what goes on. And of course, I mean, I will try to present the proof now. And of course, all the credit goes to Mukai sensei, and all mistakes are ours. Okay, so let me give you an idea of proof. So our proof goes in 4 steps. So the first step is a construction of a Yeah, so this was already explained by Mukai that the statement is about Fano threefold, but the crucial object to consider is a general anti-canonical section of this threefold, which is a K3 surface. So in fact, the first two steps of our proof are concerned with K3 surfaces, and actually the most part of the work is done with them, and then you prove a similar result for K3 surfaces, and then you extend it to higher dimensions. So the first step of the proof is the construction of what we call Mukai bundles on K3 surfaces, and what we call the Gushel map, the Gushel morphism. I will explain what's that. The second part is a proof of a similar result for K3 surfaces. So let me call it theorem A, and this will be theorem B. And it tells you that if SH is a polarized K3 surface, and I will assume that the picard of S is generated by H. So it is sometimes we call this prime K3. So this assumption, again, of genus G, where the genus is defined similarly, you take the square of polarization and write it as 2G minus 2. Then S is again mg intersected with pg. You just take a projective space of dimension by one less. That's the second part, the second step, and in some sense this is the most important step. Then the third part of the step is that you extend the Mukai bundle and the Gushel morphism from K3 to your Fano threefold. And here, if you try to extend it, then it is easier to extend the Mukai bundle not to a vector bundle, but to a reflexive sheaf, and the Gushel morphism not to a regular morphism, but to a rational map. But that's enough. So extend should be taken with this grain of salt, and and the fourth part is to extend this description. And in the fourth step, we will be able to prove that the reflexive sheaf that we constructed at the third step is actually a vector bundle, and the rational map is a regular map. So that's the plan, and let me say that if you follow this plan, then you can actually prove a slightly more general statement. Maybe let me call it theorem A prime. That the same is true is if X is a, say, Gorenstein, as Mukai mentioned, Fano threefold with terminal factorial singularities. And factoriality is essential completely essential here. Again, of the same genus. Then the same is true. Yeah. Yeah. Absolutely. This is also crucial. Yeah. Yeah, and also you can extend the same result to higher dimensions with the same assumptions about the Picard group and about the singularities of X, but the statement becomes more complicated. For instance, if you have a four-dimensional variety of that type, you can take a cone over it, and it still will have similar singularities. So in higher dimensions, you should also consider cones. So that becomes the statement more messy, but essentially this is the same result. So, sorry? You mean the high dimension? Actually, it tells you that every variety has precisely this form. No. Wait. So, as I mentioned, this is actually a very good question. And this is the part of the story which we don't understand fully yet. So, as I mentioned, this variety depends on the choice of a three-dimensional space of skew-symmetric forms. And of course, if you take a very bad family, then the variety that you will get here, it may have a dimension higher than 3, and I mean, it may be very bad. So you need to impose some genericity assumptions about the family. So one very natural assumption to impose, and which is definitely absolutely necessary, and we will see it in the proof, is that all skew forms in this family have the maximal rank 6. If you impose this, then already it follows that this variety is a three-dimensional and local complete intersection. Then in one of Mukai's papers, there was a criterion for the smoothness of this variety in terms of this space of skew-symmetric forms. We didn't manage to prove this. So if you remember how to prove this, then we will be. I understand. That was so long ago, but I mean, so far we didn't manage to recover this proof, which is a pity. Yeah, but at least we can check that these varieties are nice. I'm pretty sure that there are singular varieties among them, but this part of the story we don't understand fully. Okay, so that's our statements, and this is our plan. Now let me explain as many steps as I will have time for. So step 1. What is a Mukai bundle, what is a K3 surface, and what is a, sorry, of course I want to explain what is a K3 surface, what is a Gushel morphism. Okay, so let SH be a polarized K3 surface of genus G, and assume that I have a factorization of the genus as a product of two integers. And the factorizations that I have to consider here is 2 times 4, 3 times 3, 2 times 5, and 3 times 4. Of course, you can ask what is the factorization for 7. There is no factorization, but as Mukai explained, in this case you have to, this is the phenomenon related to the divisibility of the restriction of the Plücker class from the ambient Grassmannian. So you have to consider, in this case, the double polarization of S. So you replace H with 2H. Then if you compute the genus with respect to this double polarization, it will become 25. and 25 has a very nice factorization. This is 5 to 5. So let me write it like that. Of course, this is not true, but maybe I should write 4 times 7 minus 3 equals 5 times 5. Yeah, so this is the important equality here. Okay, so let us fix such a factorization, and then a Mukai bundle on S is a H-stable bundle with rank R, C1 equal to minus H, and the Euler characteristic equal to R plus S. Or equivalently, the Mukai vector of this vector bundle, I will denote it by U sub S, is R minus HS. And why these vector bundles are interesting? Actually, they are interesting for many reasons. One reason is that such vector bundles are spherical. Spherical means that if you compute X groups from US to US, so this algebra is isomorphic to the cohomology of a two-dimensional sphere. Yeah, I forgot to say we work over C. It is a very interesting question if these results extend to positive characteristic. We don't know so far, but hopefully one day we will solve this too, but that's very, very far from realization. Okay, and so anyway, these objects are spherical, and the spherical property is a kind of K3 analog of exceptional property for Fano threefolds. So for instance, if you have a Fano threefold and you have an exceptional object on it, you restrict it to any anti-canonical divisor, and then you get a spherical object. So this is a very useful property. We never use it in our proof, but that's just for context. What else? Maybe another thing is that the unique, actually it is very easy to see that if a Mukai bundle exists, it is unique. This is a very standard argument. Just you imagine that there is a second Mukai bundle, then you by using this, I mean, if the second bundle has the same Mukai vector, then the Euler characteristic of X spaces between these two vector bundles is the same as from the bundle to itself, so it is equal to 2. And by third duality, that means that either you have morphism between these two vector bundles in one direction or in the other direction. But since both are assumed to be H-stable, it follows that they are isomorphic. So this is very standard and straightforward. And this is very useful. So the main question is, how can one construct such a vector bundle? Again, there is an abstract approach to this question. For instance, because of this property, because these bundles are rigid, they deform well with K3 surfaces. So to construct something like that, you can first construct such a vector bundle on your favorite K3 surface of a given genus. For instance, you can use some elliptic surface and use geometry of elliptic curves to construct it. And then you can consider the relative moduli space of K3 surfaces endowed with these vector bundles, and then by deformation arguments you can extend the construction to any K3 surface of given genus. But again, there is a minor problem. One minor problem is that this only proves you the existence of a semi-stable bundle, right? So you cannot be sure that it is stable unless you know something about the Picard group of this K3. This maybe is okay, but the other thing is that you cannot really control the properties of this vector bundle. And the property that we will get, that will be very useful for us, is that the dual vector bundle is globally generated. So in a minute I will explain another construction which gives you global generation for free, but if you use this abstract deformation argument to construct US, then I don't know how to prove that the dual vector bundle is globally generated. So it's really useful to have a more direct construction of these vector bundles. If you assume that the Picard rank is 1, then of course it is stable. But still, I don't know how to prove.
Why can't you apply Lazarus construction?
This is what we will do. Okay, indeed. So the most useful construction here is the Lazarus construction. So assume my K3, assume there is a curve in this linear system which is Brill-Noether-Petri general. So if, as Gabi mentioned, if we assume that the Picard group of S is generated by H, like we do in theorem B, then actually a general curve in this linear system is Brill-Noether-Petri general. But a Brill-Noether-Petri general curve may exist in a more general situation, and it is actually important for our step 3, for the extension of our of the Mukai bundle to a 3-dimensional Fano. So what does Brill-Noether-Petri general mean? So this is a very classical thing. So if you have a smooth projective curve, you can look at the components of the Picard scheme that parameterize line bundles of a given degree, and then inside peak D of your curve C, you can consider the strata that corresponds to line bundles with given H0 and H1. These are called Brill-Noether loci. For each of them, you can compute the expected dimension, and the Brill-Noether-Petri generality means that every such locus is smooth of expected dimension. So this means that Brill-Noether loci in peak D of C are smooth of expected dimension. Yes, in fact, we don't need all of them. We need one which I will write down in a minute, and we also need to know that some of them which have negative expected dimension are empty. So by using this Brill-Noether-Petri generality, we can, applying this, we can see that there is a pair of line bundles, psi eta, on C, such that H0 of psi is R, H0 of eta is S, and psi tensor eta is the canonical class. So a line bundle and it's a joint line bundle which have these dimensions of H0. And indeed, as Claire mentioned, they belong to the Brill-Noether locus, which has expected dimension 0. So the expected dimension for such locus will be G minus R times S, exactly. So this is a zero-dimensional locus, so in fact, there is a finite number of choices. And you can even tell what number this is. This is the degree of Grassmannian R, comma, R plus S. So there are quite many choices in general. So you start with such pair of line bundles, and then you apply the following construction. So let me denote by J the embedding of my curve into my K3 surface. Then I can push forward Xi along this map. Then I can take the vector space of dimension R that of global sections, take the trivial vector bundle on K3 with this fiber. There will be a morphism, and in fact it will be surjective, so you can check by using the Brill-Noether generality that both Xi and eta are globally generated. Because if they are not, then you can easily construct a line bundle which would violate Brill-Noether generality just by a standard construction. So they are globally generated. We have a surjective morphism like that. And the kernel is, of course, a vector bundle of rank R. You also easily compute that its C1 is minus H, minus the class of the curve C. And it's also easy to compute the Euler characteristic. So that's the vector bundle with the properties that you like it to be. And also you can easily check that the dual vector bundle is globally generated. To do this, you just dualize this exact sequence. So this is a torsion sheaf, so its dual is 0. Because of that, you start with the dual of this bundle. Then you have US dual. And then local X1 here, it is also easy to compute, and this is just the push forward of eta. And now you see that this is a globally generated vector bundle, this is a globally generated coherent sheaf. This bundle doesn't have first cohomology, so it follows immediately that this vector bundle is globally generated. It also follows that it doesn't have higher cohomology. And its cohomology is C to the power R plus S in dimension 0 and no higher cohomology. So R comes from here, S comes from here, so altogether you have R plus S global sections. Okay. Yes. Yeah. Now, what can you prove? So you can prove the following. Yeah, I mean, all these properties are clear. What is not completely clear is why it is H stable, right? And here is our first result is that, I mean, the first part is very easy, but let me still mention it, that if the Picard group is small, then, of course, it is stable. This is very easy just because if you compute the slope of this vector bundle, it is -1 over R, and this is the maximal possible negative slope. So everything which would destabilize this vector bundle would have non-negative slope, and because this is a semi-stable sheaf of slope 0, you have no room for destabilization. So this is really very easy, and the more complicated, but useful for the extension result is an explicit criterion for stability. So let me say it. We don't prove it in full generality, we only prove it for small values of R. So note that here we have, so the first factor is always quite small. It is 2 or 3. So for these cases we can prove it. So we will always assume that S is greater or equal than R, and R is 2 or 3 only. Then US is, say, not H stable if and only if there is a class in the Picard group of C which extends this small psi from the curve. And also its cohomology also extends the zero cohomology of psi. So you have R-dimensional space in H0 and no high cohomology. So this is a very explicit result. And let me also mention that we also prove it in the case where S is not smooth, not a smooth surface, but a surface with dual singularities, which is very important for the extension result in step 3. There was some question? No? Yeah. Thank you very much. Yeah, absolutely. This is S. Yeah. Great. Okay. Actually, I think I don't have time to explain this second part, but this part is already in the archive, so you can look it up if you want. Let me just mention that because, as we assumed, our linear system contains a Brill-Noether general curve, it follows that the corresponding Picard surface itself is Brill-Noether general, and this argument heavily uses this Brill-Noether generality of the K3, which, by the way, was also introduced by Mukai. So you see everything here is introduced by him. Okay, so that's the first important result in this direction. And now what you do. So you have a globally generated vector bundle. So it gives you a morphism to the Grassmannian. So US gives you a morphism. We denote it by gamma S from S to Grassmannian of R-dimensional subspaces in a vector space of dimension R plus S. And this is what we call the Gushel morphism. Okay, now actually if you are willing to assume this smallness of the Picard group of S, then then everything can be done for any genus. In our theorem B, we use these particular values of the genus, but the construction of a Mukai bundle in this case and the construction of the Gushel morphism, they are absolutely general. You can do it for any genus as soon as you have a factorization of the genus as a product of two integers. You always have this morphism. And you also can check that, also a nice thing, that this morphism is always a closed embedding. If we have this assumption, and also, of course, by construction of this morphism, if you pull back the Plücker polarization from the Grassmannian, you get your polarization of K3, and so it follows that S at least is contained in the intersection of this Grassmannian with PG. So it follows immediately. Okay, now actually you need to prove that this is not just an inclusion, but first of all that these vectors through the intersection of one of these Mukai varieties with PG, and that it is not just an inclusion, but that this is an equality. This is the second part of our theorem, of our plan. Okay, maybe I want to keep the plan and theorem B for a while. Okay, step 2. How do we prove theorem B? Here we have two nice observations, which are maybe the main input that we bring into this subject, which are two simple lemmas. And these are the simplifications that I mentioned. So the first lemma is very simple. So it tells you that if, and again this lemma is true for any genus. If you have this prime K3 and you construct this Gushel morphism, then the image of the Gushel morphism does not lie in any Schubert divisor. The morphism given by this vector bundle. So it does not lie in any Schubert divisor. You know, if you consider Grassmannian, right, it sits inside the Plucker space of a big dimension. You can take hyperplane sections of your Grassmannian. Some of them will be smooth, some of them will be singular, but there is a distinguished family of Schubert hyperplane sections, which are the most singular hyperplane sections of the Grassmannian. They are parameterized by S-dimensional subspaces in your R plus S-dimensional vector space. I will usually denote it by V. So this is V. So if you have S-dimensional subspace in V, then it gives you the following divisor. You can consider all R-dimensional subspaces in V, which have non-zero intersection with Vs. It's easy to see that this is a divisor and it is linearly equivalent. I mean, it gives you a hyperplane section of your Grassmannian. So you have a family of such divisors parameterized by this dual Grassmannian, S, R plus S. And the claim is that if the Picard number is 1, then your K3 is not contained in any of these Schubert divisors. And the proof is very simple again, because actually, as you can see from this definition, from the very definition, a Schubert divisor is a degeneracy locus, right? You have a, say, you can consider the trivial vector bundle with this fiber. It sits inside the trivial vector bundle with fiber V, and then you can project to the quotient of V, to the quotient of V by the Mukai bundle. So you can consider this composition, and if gamma of S is contained in such a Schubert divisor, this means that this morphism is everywhere degenerate. And if it is everywhere degenerate, then you can look at its image and you can see that it destabilizes this vector bundle immediately. Again, because the Picard number is small, and so it's easy to control the stability. Maybe I should have mentioned that this vector bundle is also stable. And this is actually the dual of a Mukai bundle of type S, R. So we had Mukai bundles of type R, S, and this is you can always switch the role of S and R. So this vector bundle is also stable, and so it's very easy and completely standard to deduce from the stability that this morphism cannot be everywhere degenerate. That's very easy, but very useful, as you will see. And the second useful lemma, which works very nice in a combination with this first lemma, is the following. So assume that, let us consider any intersection of the Grassmannian with PG. So let us choose absolutely arbitrary PG and let us intersect with the Grassmannian. And of course I assume that G is R times S, as usual. Then also assume that somewhere it has a tangent space of dimension bigger than 3. Assume there is a point in this Y such that the dimension of the tangent space is at least 4. Then Y is contained in a Schubert divisor. And actually, this is also very simple. You just count parameters. That's like very simple observation. But it is very useful in combination with this one, because so we know that our K3 sits in a linear section of precisely this form. So it tells you that the intersection, eventually we want to check that S is equal to this intersection. But what these two lemmas tell you is that if it is not the whole intersection, then the intersection is not too big. It cannot have dimension bigger than 3, because of course then there will be points with big tangent space. And if by chance it is 3-dimensional, then it must be smooth. You see? So if it has bigger dimension than you expect, then it is automatically smooth, and this is very useful. Okay. Any intersection, absolutely.
What's VS? So it's for a flag.
For some S-dimensional subspace. Yeah. So it tells you that if such an intersection has tangent space of big dimension at least one point, then it is contained in a Schubert divisor. There is a Schubert.
Why is expected one point?
No. So if you replace the Grassmannian by one of the Mukai varieties, yeah, on that table, then the expected dimension of such an intersection is 2. Mukai varieties themselves, they are also linear sections of Grassmannians, but highly non-transverse. So the expected dimension here is typically negative.
Here you could have an intersection of dimension 4, in which case the condition becomes vectors.
Where?
And then you are saying that it lies in the Schubert cycle.
Yes. Yeah. That's the point. Yeah. Mm-hmm. Okay, maybe let me mention one more small lemma which is used in the proof, but maybe it doesn't have so much meaning, is that if 1 over R plus 1 over S is bigger than 1 over 2, then if you consider the pullback to S along the Gushel morphism of the co-normal bundle of the Grassmannian inside the Plücker space twisted by 1, then this is 0. This is also not hard to prove, just because there is a natural filtration on this vector bundle, which is given more or less by tensor products of wedge powers of the Mukai bundle of type RS and of type 1 of type SR by this pair of Mukai bundles, maybe up to some twist. And then you can check that, yeah, of course, such tensor products are semi-stable and you can compute their slopes. And this condition ensures that all the slopes are negative, so you cannot have global sections by semi-stability. And you can see that for these factorizations, this inequality always holds, right? Of course, when one of the factors is 2, it's obvious, and it is also okay for 3,3 and 3,4. And it is also okay for 3,5, but there is no case here. Okay, yeah, so now we can prove theorem B. Yeah. First of all, we need to check that, where is theorem? So it's here. We already know that S is contained in the intersection of Grassmannian with PG. But we want to check that it is inside, yeah, inside this intersection. So this is what we want to check. Of course, for this we need to recall the definition of MG. So the point is that MG, in all these cases, it is in the terminology of Claire, which I don't like very much, but let me use it. This is CBS. You write CBS, right? For some very special, sorry? Okay. Okay. In the terminology of Collar, this is CBS for explicit vector bundles. So when G is, so the best case is for genus 8. In this case, this vector bundle is 0. I will denote this vector bundle by E0. For G equal 9, E0 is wedge 2 of the dual tautological bundle on the Grassmannian. For G10, E0, you take the perpendicular bundle on the Grassmannian and twist it by 1. Yeah, by the way, this is U twisted by 1, which may be a coincidence, but it looks like not really a coincidence. And here, this is a direct sum of 3 copies of this guy, because we consider 3 skew forms. So, in each of the cases, you just take a global section of one of these vector bundles, and non-degenerate global section in a precise sense, and then its 0 locus has expected codimension, and this is precisely MG. So, what does non-degenerate mean? So here, of course, it means nothing. Here, a global section is a skew form on a 6-dimensional vector space, and non-degeneracy is just the usual non-degeneracy of a skew form. Here, a global section is a 2 form on a 7-dimensional, a 3 form on a 7-dimensional vector space. And it is a classical fact that the group GL7 acts on the space of 3 forms on a 7-dimensional vector space with an open orbit. And non-degeneracy is precisely the assumption that the point belongs to this open orbit. And by the way, in this case, the stabilizer of this form is exactly the group of type G2, so it's important. And for genus 12, the assumption is the one that I mentioned, that every skew form in this 3-dimensional space has the maximal rank 6. So, each of these Mukai varieties is the 0 locus of a global section of these vector bundles. So if we want to check such an inclusion, we need to check that a non-degenerate global section of this vector bundle vanishes on the K3. And there are two steps. So the first step is to prove that some global section vanishes, and the second part is to prove that this global section is non-degenerate. And the first part is relatively easy, because you just need to compare the dimension of the spaces of global sections on the Grassmannian and on the K3. So on the Grassmannian, of course, you know everything. And on the K3, you can compute the dimension of the space of global sections if you know the vanishing of Hayek homology, right? Because then it is given by the Euler characteristic, which is easy to compute. And indeed, we can check that the Hayek homology vanish in this case, so it requires some effort. And for instance, maybe let me mention that this vanishing of Hayek homology can be interpreted in terms of the Lazarsfeld construction, and it is equivalent to the surjectivity of the natural map of this sort. And similarly for eta. And I don't know, I would expect that there are some general results of this sort. Then you will tell me. Yeah, in the cases that we are interested in, we can prove it also, but yeah, I would expect that this is known, indeed. Okay, so the Hayek homology of the bundles that we are interested in vanish. So the dimension of the space of global sections on the K3 is less than on the Grassmannian. Therefore, there is an appropriate global section on the Grassmannian that vanishes on the K3. But how do you check that it is non-degenerate? That's, that part of the argument always puzzled me when I was young. Of course, you can try to say, imagine it is not non-degenerate, then that means that your K3 is contained in some degeneration of a Mukai variety of this MG, and then maybe you can arrive at some contradiction. Actually, say for genus 9, you can indeed argue like that, because there are not so many possibilities for a type of a skew form on a 6-dimensional vector space, right? It can be non-degenerate, it can be of rank 4, it can be of rank 2, and that's it. But for instance, if you look at the genus 10 case, fortunately orbits of GL7 on the space of three forms are classified, but there are many of them. And it will be a nightmare to check for each of them that this cannot happen, except for the general one. But fortunately, this lemma gives you the result immediately. You can very easily check that if you have a section of these vector bundles which is degenerate, which is not a general one, then the zero locus is contained in a Schubert divisor. So for instance, if you take a skew form of rank 4, it is like, you can write it as a direct sum of two decomposable two forms. You just wedge it with an appropriate linear form so that it becomes decomposable, and then you see that it sits in this Schubert divisor. It's a bit more complicated in this case, but again, fortunately, there is a classification. Representatives of all orbits are written down. They can be found on the archive, and it's immediate to check that each of them, except for the general one, is contained in a Schubert divisor. So this step that could be a nightmare, with the help of this lemma, it's very easy. I guess I'm out of time, right? Am I? How much time can I have? I can go on. So, 45? 2 minutes. Okay. Okay, then The only thing that I will manage to do is maybe to say 2 words how we finish the proof of this theorem. So, yeah, now we know that S is contained in MG intersected with PG. And now, as Gabi mentioned, this intersection has expected dimension 2. It contains a surface. So either and also this variety is connected. This is a linear section, it is also connected, right? So there are 2 possibilities. Either this intersection is 2-dimensional, or by this lemma, it is a smooth threefold, right? There are only two options left. If it is 2-dimensional, then it's easy to compute its degree, and its degree is exactly 2g minus 2. So then in this case we have an equality. So the only thing left is to check that the case where this is a smooth threefold is impossible. So let me denote this by y as before. This is a smooth threefold. And we have to show that this cannot happen. So we had this vector bundle E0 such that MG is CBS for it. Let us also take E, which is a direct sum of E0 and a few copies of O of 1, such that its 0 locus is this Y. And then if this is a smooth threefold, that means what? So we have a global section here, so a global section of this vector bundle on the Grassmannian, sigma. And we have the differential of this sigma that goes from the dual vector bundle of E to the conormal bundle of S in Grassmannian. And these 2 vector bundles have the same rank and the same first Chern class. And if the intersection is a smooth threefold, then this map, this differential, everywhere, probably I should write this pullback here. Yeah, this differential everywhere has corank 1, everywhere. So its kernel and its co-kernel are line bundles. And they are line bundles of the same degree. So you have an exact sequence like this. For some t, for some integer t. Remember that the Picard number is 1, so we don't have too many possibilities for these line bundles. And you can also easily bound this t. So because this bundle is a direct sum of stable line bundles and you know the slopes, it gives you one bound. It tells you that t is at least 1. And because this bundle, if you twist it by 2, it is globally generated because S is an intersection of quadrics. That's a classical fact. Because of that, t is not greater than 2. So there are 2 cases. This may be only 1 and 2. And if it is 1, you can obtain a contradiction with this equality. This is precisely to show that the case t equal 1 is not possible. And so assume that it is 2. So if t is 2, then then it is easy to conclude that S is in fact a complete intersection of this smooth threefold with a quadric. So this is what you can conclude from t equal 2 very easily. And then if you know this, then you can take an intersection with an extra hyperplane, a general hyperplane. Then you will see that a Brill-Noether general curve C is an intersection of some smooth projective surface, again with a quadric. And you can easily check that this contradicts the Brill-Noether generality. In this case, R must be either a Delpezza surface, and then C is a double anti-canonical curve on it, and then it's easy to see that there is a linear system here which contradicts the Brill-Noether generality, or it can be a smooth elliptic scroll, and then you also have a linear system which contradicts Brill-Noether generality. And that's it. Okay, let me stop here, and if you ask, I can tell you more about steps 3 and 4. Thank you.
So to prove you're an A or A prime, you start by taking a general and canonical section, right? How do you get the Picard assumption that you're using? Because you don't have that.
Actually you do. There is a paper by Ravindra and Srinivas that does exactly what we need. Ravindra and Srinivas. They have two papers. So one paper tells you that if you say start with a fourfold and take a general linear section, then the restriction morphism on the class groups is an isomorphism. So this is enough to go from any dimension to dimension 3. And the second theorem is to go from dimension 3 to dimension 2. It is called Noether-Lefschetz theorem, blah, blah, blah. I don't remember the precise title. So Ravindra Srinivas, very useful result. Yeah. And it is nice that they work they allow singularities and so on. They have a necessary condition. So essentially, this is not necessarily for K3 inside Fano. So if you have a threefold and a morphism to a projective space such that the push forward of the canonical class twisted by O of 1 is globally generated, then they have this result. And for genus at least 4, it is okay. Maybe non-transverse, right? That, yeah. I think if this would, no, at least I definitely don't know, except for some cases which were described.
But this is for a general. Yeah, general.
Is it known? So it's not known to Gabi, so probably it's not known. I don't know, yeah. Yeah, and another similar question is maybe you could ask, so 12, we use the factorization of 12 as 3 times 4. There is another factorization as 2 times 6, right? So what happens in this case? Are there explicit equations? We don't know. Do you know? Unfortunately, yeah. Another thing is that...
so 12 by 6, so there is no Fano threefold here?
That's the same Fano threefold.
It's the same Fano.
Yeah. I mean, the same Fano threefold also has a morphism to Grassmannian 2-8.
So you have another realization.
Yes, but we don't know how to describe it inside. The question is, do you have a CBS or something like that? For this embedding, we don't know. If you are interested in Fano threefolds in characteristic P, you know, this theorem in characteristic 0 is extremely useful. If you are interested in Fano threefolds in characteristic P, then something like that would be also useful.
A lot of the steps that are one in the, I don't know about step 3 and 4, those are probably knowing arbitrary parameters.
How do you construct an anti-canonical section with Picard number 1?
So the questions are, you need to do it for every K3 or you can relax inside of it?
Yeah, that's a very good question. Yeah. So indeed, we mostly work under this assumption. Why? Because we can, right? In a more general situations, we wouldn't be able to do so. So the question is, can one relax this condition to something weaker? And we believe that you can replace this by Brill-Noether generality for the K3. And in one of Mukai's papers, it is also explained. But this part we cannot prove. For instance, the Lazar's-Feld theorem, which we use a few times, it is only
Everything that you said here, when you replace pk number 1 by a general K-free surface in the moduli space, if you had that sequence of statements, would that be enough to conclude? Because that I think is possible.
you mean to replace Brill-Noether generality just by generality,
Because is z times 8.
by implicit generality? I don't know. We did try to replace it by Brill-Noether generality. I mean, we didn't spend much time on that, so maybe this is possible, but with some implicit generality. It may work. We don't know. At least I don't know. Thank you.